Welcome you all for today's NPTEL online course on Smart Grid. And during last lecture, we were discussing about the execution of the Smart Grid concept on an laboratory scale of hardware setup. We have seen the different facilities available in the laboratory, and we were talking about how a DC microgrid can be simulated at 3 different operating conditions, both at peak load conditions, off peak conditions, and isolated mode or islanded mode of operation. Now, during this case study, I like to explain you all what kind of time intervals have been considered, the status of the devices have been identified. During the peak mode, we have considered actually different time period like 0 to T1, T1 to T2, T2 to T3, and T3, T4, T4, 5, and 5 to end. So, we have considered different time of operation, time intervals, and these are the battery status, whether it is absent or ideal or the super capacitors operation, and these are the SOC status, whether it is 70% or greater than 30%, less than 30%, less than 20%, less than 10%, etc. And we can say the grid status when it is ideal, ideal, etc. And whether it is a peak hour, yes, it is a peak hour, peak hour, peak hour, peak hour, peak hour. Now, one point let us all understand, when we talk about peak mode of operation or peak hour of operation, means my utility is experiencing a peak hour, and whatever the experimentation we have done, we have considered that at this point of time the system is facing a peak. Okay? So, the peak condition of the system has been sensed, and based on that peak hour point, we allow our DC microgrid to operate accordingly, so that my grid will not be stress mode, and similarly off peak. But still there are a bit of challenges. How do we sense the peak period, whether the peak period based on your frequency that can be identified, or based on the pricing of energy at that given time. So, that is another challenge that need to be seen. How do you like to identify the peak hour based on the pricing or based on the frequency? But what we are focusing here, if the system is at peak, how do I have my control strategy and manage all my devices not to stress more to the utility? Now, similarly the off peak and isolated mode. Now, we will get into the hardware simulation, which is very important. I need your attention, please focus. Now, the peak hour mode, we can see there are so many characteristics. I will be interested to explain you one by one very slowly. This is my time period T1, and this is at T2 and T3, T4, T4 and T5, and this is basically the DC bus voltage. Could you see the variation? This is what the bus voltage have been bus voltage has been monitored, that is V bus, and then we can see the PV current, battery current, as well as ultracapacitor current characteristics. So, this characteristic, the green one, which is you can see this one, which is my current characteristic of the PV, and the blue one, which is the current characteristic of my battery, and the pink one is the current characteristic of my ultracapacitor. And then we will see the load which has been connected to my grid, which is the load current, which is keep on reducing. And then the main important part here, we have C6 and C7 characteristic, which is my grid voltage and current characteristic, grid voltage and current characteristics. And to see further, we have actually zoomed the B characteristic, you can see, which is the zoomed view of the first characteristic, that is A characteristic, and at instant T1. So, we have different time instants. So, mainly this area which has been zoomed, now we can clearly see how my bus voltage looks like, and this is PV current, battery current, alter capacitor current, and further we can see the grid voltage and grid current. And we have not considered perhaps the 1, 2, 3, 4, 5 and 5 has not been, the load current has not been considered in the zoom characteristic of the B. Perhaps we can see the superimposed waveform of the grid at instant t1, these two C6 and C7, the both voltage and currents have been superimposed, just to understand how my voltage profile is varying and how the current characteristic is keep on varying. So, the basically the combination of these two. And perhaps the D, it is we have considered one more time instant, that is T5, and we have also zoomed this zone, that is T5 instant, and you can see the characteristics in detail, and C1 which is my bus voltage, and then we can see the PV current, battery current. The one significant here, you can see the battery current actually stepped up, and whereas it is again a step down depending upon different loading conditions. Okay, that has been considered, and then you can see alter capacitor and again my grid voltage and current characteristics, and those two have been superimposed just to see, and you can see the way the current characteristics behave compared to the previous one, just to understand the system perspective. And this is the way actually the peak hour mode operation being performed. And if you move to the off peak hour mode, and off peak hour mode, actually you can see this, like once again my bus voltage at off peak, and then we have the PV current, and certainly then we have the battery, and then we have my alter capacitor characteristics, and then that is a load current which is constant, and then we have grid voltage and current characteristics. And now depending upon the different cases, like case 1, case 2, case 3, case 4, at different time instant T1, T2, T3, you can see the characteristics behave from T1 to T2 and again from T3 to T4. Now, in case of isolated mode, we can clearly see my grid is actually absent. So, when my grid is not there, that means both the C6 as well as C7 they are not present, because grid is not available to me, and it is just within the microgrid we have captured the bus voltage, DC bus voltage, and then we can see the PV current as well as battery current, alter capacitor current as well as load current. These 5 characteristics have been tapped, and that is what actually the first characteristic A look like, and whereas the B and C are the zoomed characteristics of my T3 and T4. So, we have considered, previous case we have considered T1 and T5, now we are talking about both T3 and T4. So, this area as which has been zoomed here, and this area which has been zoomed here. So, we can clearly see especially if you focus the battery which is not varying much, sorry, the PV is not varying much, whereas the battery drop down. In case of T4, you could see the PV is gearing up, whereas the battery which is in the same way similar to my previous T1 scenario. And above and all, when it is the grid is not available, the whole energy has to be met within the system, and certainly we have to curtail some of the non-critical loads as and when the battery SOC goes down, and step by step we can curtail the non-critical loads to manage your energy scenario. Further, we have considered a interconnection between two DC grids. If you remember, in my simulation we have considered two DC grid, one is at 380 volts, the other at 48 volts, and we try to control the scenario of having two DC grids. And now in case of this case study, we have considered one microgrid. They are autonomous microgrids, and during practical implementation we have considered one grid at 48 volts and the other grid which is at 100 volts. Now in case of inter-DC grid power flow, bidirectional power transfer between two autonomous DC microgrids, and the autonomous DC microgrid, the first microgrid allowed to operate at 100 volts, whereas the second DC microgrid allowed to operate at 48 volts. Both the microgrids are autonomous, and you can see the experimental results of two microgrids. We have considered the time zone T1, T2, T3, T4, T5 and T6. Now for better understanding, we can see there are two VA, that is the first grid, and this is my second characteristic, that is VV, the green one, and the first one, the I1 represent my autonomous grid number 1 and I2 represent my autonomous grid number 2. So similarly for both the grids we can have PV characteristic for the first grid, battery characteristic for the first grid, load characteristic for the first grid, and similarly battery, PV and the load characteristic for the second microgrid. So we do have two microgrid in place. During theory we have discussed two microgrids are of two different voltages. One is at 380 volt, the other is at 48 volts, and the simulation strategy has been discussed. But during the practical implementation, instead of 380 volts, we scaled down to 100 volts, and the second grid is 48 volts, and then we performed both the grid simultaneously. And then one more setup where we thought of expanding the microgrid scenario to a larger scale, the impact of microgrid or a smart grid into a national grid perspective, where we assume that there are hundreds and thousands of microgrids may present in future, and what sort of impact that the national grid can visualize. We have seen if the system is at whether it is a peak condition or off peak condition, or there is no grid available to me, my smart grid has to manage its energy within itself. Now if you take the Indian grid at large, so this is my Indian grid, and at a particular point of the one of the bus of that Indian grid, we can come down to the distribution level, and that bus we can connect our DC microgrid with help of real time simulator as well as power amplifier. Now the same setup, closed loop setup, we have, let us say, your real time simulator, and then we have your power amplifier, then we have the device on test, all right, and further we can give a closed loop signal to my real time simulator. And I am not whereas focusing here the conversion between digital to analog and further analog to digital conversion before giving back to my RTDS. Now, this is what actually the test bed which represent my device on test, and this is what my amplifier look like, and this is what my simulator is all about. Now, the concept is the point of selection is one point of the national grid where we experiment this, and we repeat this kind of setup at each and every bus of the national grid to see the overall impact of energy management at each and every microgrid, how it can really enhance the system capability at a national level. And we have considered one case study, that is case study number 3, where the DC microgrid of our laboratory has been integrated with the IIT Roorkee distribution system. In case of reduction of the Indian network, if you look at the Indian network at large, which is a very huge, and simulating Indian network within our simulator capability is impossible. That is why we try to reduce the all India network transmission system to a reduced system, so that that system can be simulated or burned within my simulator, and at one transmission bus, scaling down the voltage to a distribution bus, we can integrate the IIT Roorkee network, and further within the IIT Roorkee network at one bus electrical engineering department, we can integrate our DC microgrid and see the overall impact, changing the behavior of your DC microgrid control by adjusting both battery, ultracapacitor and PV emulator as well as load, how we can see the impact of managing the peak scenario faced by the utility or the system. Now, we have considered the all India peak of 2013 during the month of August, and we found that over 280,000 circuit kilometer of the transmission network at different 5 zones, and truly the Indian network, which had 6,034 buses, out of which 575 buses had generators and 3,422 buses had loads, and altogether there were 8,116 transmission lines, and simulating such huge network having 6,000 buses were impossible. So, an attempt has been taken by the research team of this laboratory to reduce that network to a smaller scale, so that at least we can simulate the all India network with the simulation capability available in our laboratory. Now, the net generation at that point was 120 gigawatt approximately, and the load was 117 gigawatt. Now, this is how my network look like. So, this is the original all India network, which had approximately 6,000 buses, and this network through rigorous simulation have been reduced to a network of 120 nodes with 216 lines. So, what we have done basically, each and every zone have been squeezed to a single node based on certain algorithms, and then now my all India system is being represented by 216 lines and 120 buses. So, it is easy for me to simulate 120 bus all India network instead of going for 6,000 buses at large. We have also analyzed the feasibility study of DC microgrid integration to IIT Roorkee distribution system, and the practical IITR distribution system is modeled within RTDS, and we have taken the practical data of IIT Roorkee system and simulated within the RTDS, and you can see without the DC microgrid and DC microgrid interface, you can see the different voltages at different buses of the network, and it has been felt that having DC microgrid interfaced, certainly we can improve the voltage profile of the system. A significant improvement at bus voltage profile and effective utilization of PV is observed with help of DC microgrid integration. Optimal power flow of the lines is also achieved by optimizing the placement of DC microgrid. The DC microgrid can be placed at different locations. So, by varying the location, we felt that optimal utilization of the lines as well as the voltage profile can be achieved. It is a runtime window of IIT Roorkee system. I mean, this is what the pictorial view of IIT Roorkee campus, and this is my network. We can see this radial, but we have many rings in between. And this is without the DC microgrid. And then further actually we have integrated DC microgrid and carried out PHIL experimentation of IIT Roorkee campus along with DC microgrid interfaced. We have also performed a couple of case studies on coordinated voltage control, and in which we had the utility, which is the utility grid. Then we have taken a distribution system of 33 bus, and then you can see the DC microgrid which has been interfaced to a IEEE distribution system and connected to my utility. And the DC microgrid, which has 1.7 megawatt of load and then 0.4 megawatt of battery and 1.8 megawatt of PV, which is at the simulator level, but they have been scaled down 1000 times to realize in the laboratory scale. And this is what the setup look like in the laboratory. Just to emphasize, you can see the RTDS here, amplifier, we have PV emulators, DC loads, battery and ultra capacitor, DC-DC converters, sensors, DC-AC converters, oscilloscopes and transformers. This experimentation, the very interesting part, as I told you, this is the amplifier and the signal which has been fed to my setup, which is a device under test. After receiving the signal in the digital form, and then we convert that D to A, give to my amplifier and then feed back to my system, and then the further analog to digital conversion, and it can be given back to my RTDS. So, this is basically a closed loop PHIL experimentation setup. And once again, similar to the previous discussions, we can see the characteristics, power characteristics for both PV and DC microgrid. The proposed voltage control, then existing and without CVC, different comparisons. So, finally, it has been claimed that with help of DC microgrid, certainly the coordinated voltage control can be achieved better compared to a system without having a microgrid. With this, we come to an end of today's lecture. Overall, I like to emphasize that we have discussed on the hardware implementation of the cases that have been discussed earlier during previous lectures, where we simulated many case studies. Then we took those concepts or ideas into simulation level first, and then we executed on a hardware setup. Though there are a bit of challenges, but fortunately all the simulations for energy management and then integrated with the IITR Roorkee distribution system, interfaced with All India network and coordinated voltage control schemes have been very perfectly executed with help of a DC microgrid in place. Thank you very much and good luck.